Welcome to section 3.2, graphing polynomial functions. Objective 1, graph a polynomial function. So in our first example here, we're asked to graph the polynomial function f of x equals the quantity 3x plus 1 times x minus 2, that quantity squared. The first thing we're going to do is determine the end behavior of the graph of the function. Okay? And so finding the end behavior first helps us to know what the graph should look like before beginning to graph it. So to help us, we need to find our leading term. So since our f of x is written in factored form, we need to write it in expanded form. So let's expand f of x. So we have f of x equals 3x plus 1, x minus 2. So let's expand x minus 2. Oops, that should be a minus 2. Okay. So then we would have 3x plus 1 times x squared minus 4x plus 2. Then when we multiply these together, we have 3x cubed minus 12x squared plus 6x plus x squared minus 4x plus 2. So in combining like terms, we'll have 3x cubed minus 11x squared plus 2x plus 2. Okay. So our degree for our polynomial is 3, and our leading coefficient is positive. So our end behavior will look something like that. It's going to resemble the graph of x cubed. All right, so as x approaches negative infinity, y is approaching negative infinity, and as x is approaching positive infinity, y is approaching positive infinity. So now let's do step 2. And step 2 tells us to find the x and y intercepts of the graph of the function. So to find the y-intercepts, we are going to set f of 0. Well, we're not going to set it to anything. We're going to evaluate it. I was like, that's the x-intercept. For the y-intercept, we're going to evaluate f at 0. So we will substitute all x values for 0. Well, that's 3 times 0 plus 1. And then 0 minus 2 squared. So that's going to be 0 plus 1 times negative 2 squared, which is 1 times 4, which equals 4. And our x-intercept, we are going to now set f of x equal to 0 and solve. So 0 equals 3x plus 1 times x minus 2 squared. So we can use the 0 product property to set each factor equal to 0 and solve for x. So 3x equals negative 1. So x equals negative 1/3. And then for x minus 2, x equals 2. So for our y-intercept, we have the point 0, 4. And for our x-intercept, we have the points negative 1/3, 0, and 2, 0. Also, Step 3. Determine the real zeros of the function and their multiplicity. Use this information to determine whether the graph crosses or touches the x-axis at each x-intercept. Well, our function is f of x equals 3x plus 1 times x minus 2 squared. We know our real zeros are the x-coordinates of our x-intercepts, so the x values, so that's -3 and 2. -3 is the real zero, and it has a factor that has an odd multiplicity. So it has a multiplicity of 1, which means it's going to cross the x-axis. Now the real zero 2, its factor has a power of 2, so it's even, which means it has a multiplicity of 2, so it touches the x-axis. So now we need to determine the maximum number of turning points on the graph of the function. Well, the number of turning points is equal to n minus 1, where n is the degree. So if our degree is 3, then 3 minus 1 is 2. So we're going to have a maximum number of 2 turning points. All right, in step 5, we're going to put all the information together from steps 1 through 4 to obtain the graph of f. To help establish the y-axis scale, find additional points on the graph on each side of any x-intercept. Okay? So to help us, I'm going to draw our x-axis here. I know I have 2 zeros, -1/3 and 2. So I'm going to choose a point in each interval. That's going to be -1, 1, and 3. Okay. I know that I can utilize my calculator to help me find these values. So I need to find f of -1, I need to find f of 1, and I need to find f of 3. Remember, I didn't choose 0 because I already evaluated my function at 0 when I tried to find my y-intercept. Okay, so let's grab our calculator and we're going to go to y equals, and we're going to enter in our function. So that's 3x plus 1 times x minus 2 squared. Enter. And I'm going to go to the table so that I can determine the y values of these 3 chosen numbers. So second graph, and I need -1, so I'll move up a bit. So I see -1 is -18, 1 is 4, and 3 is 10. Okay. So I have -18, 4, and 10. So these will give me the points -1, -18, 1, 4, and 3, 10. Let's bring down our y-intercepts. Well, y-intercept only 1, 0, 4, and our x-intercepts, we had 2 of them, -1/3, 0, and 2, 0. So let's plot these points on the graph. So I have negative 1/3, 0. So let's go. And I have 2, 0. It's right here. Then I have 0, 4 there. And then my three other points, I have negative 1 and negative 18. And then I have 1, 4, 1, 4, and I have 3, 10. Okay. Now, for my x-intercepts, I know at negative 1/3, I'm going to cross the x-axis. So it's going to cross. And at 2, I'm going to touch. Oops, let's reread that. Okay. So I know then that there's going to be a turning point between these 2 points, and so I need to figure out what that will be. Since my x for the first one is 0 and my x for the second one is 1, let's try and find 0.5. Okay? So we're going to find f of 0.5. And let's use our calculator to help us. Okay? So you see here on the table, our x is going by values of 1, and I would like it to go by values of 0.5. So a change in 0.5. So I'll click second window to go to my table setup, and I want the change in the table to go by 0.5. So I'm going to change that to 0.5 and press enter, and then go back to my table, and I see here now that it's going by 0.5. So I want 0.5, and 0.5 gets me a value of 5.625. So this is going to be my turning point that I need. I can also see here that it is a turning point because it goes up to 5.6 and then it goes back down. So this is 5.62. All right. So let's go to 5.625, which isn't too high. We'll be about there. All right. And so now we have our points, so we can connect our dots. All right, beautiful. Great. And we see that this graph resembles y equals x cubed with our end behaviors, which is what we got in step 1. We have our y-intercept and our x-intercepts labeled on our graph, which was from step 2. For step 3, we identified the multiplicities of our x-intercepts, our real zeros. So we know one crossed and one bounced. And then for step 4, we identified our turning points, and we have 2 of them, one right here and one right here, which is great. And so now, using those 4 initial steps, we have graphed this polynomial function. So in summary, step 1, we determined the end behavior of the graph of the function. In step 2, we found the x and y intercepts of the graph of the function. And in step 3, we determined the real zeros of the function and their multiplicity. We use this information to determine whether the graph crosses or touches the x-axis at each x-intercept. Then in step 4, we determine the maximum number of turning points. on the graph of the function, and then we used information in steps 1 through 4 to draw a complete graph of the function to help establish the y-axis, scale. We found additional points on the graph on each side of any x-intercept. Okay, awesome. All right, so now that we have our 5 steps, let's solve one more problem, but not broken down. Ooh, but we're going to follow these same steps to help us. All righty. So here we're asked to graph this function, f of x equals x plus 1 times x plus 3 squared times x minus 4. Okay. So in step number 1, we need to find the end behavior. Okay, so that's step number 1. Find the end behavior. So we need to expand our function. Let's do that. Okay. So we are going to multiply our x plus 1 and our x minus 4 together. And then we'll multiply our x plus 3 times our x plus 3 together. So that'll get us x squared minus 3x minus 4 and x squared plus 6x plus 9. Then we will multiply all these values together. So we'll take each term in the first quadratic and multiply it by all the terms in the second. So that'll be x to the 4th plus 6x cubed plus 9x squared minus 3x cubed minus 18x squared minus 27x, and then minus 4x squared minus 24x minus 36. Okay. And so then we would have x to the 4th, combining like terms, 3x cubed minus 13x squared minus 51x minus 36. So that is our function in expanded form. So our leading term is x to the 4th. So this means that we have a degree of 4 and our leading coefficient is positive. The graph is going to resemble y equals x to the 4th. So our end behavior is going to be going towards positive infinity. Okay. All right. Step 2, we are going to find our x and y intercepts. So for our y-intercepts, we'll evaluate f of x at 0. So f of 0 equals 0 plus 1 times 0 plus 3 squared times 0 minus 4. So that's 1 times 3 squared times negative 4. So that's 1 times 9 times negative 4, which equals negative 36. Our x-intercept, we are now going to set f of x equal to 0. So 0 equals x plus 1 times x plus 3 squared times x minus 4. So we'll set each of these factors to 0. And so x equals -1, x equals -3, and x equals 4. Okay. So we have a y-intercept of 0, -36. And we have 3 x-intercepts at -1, 0, -3, 0, and 4, 0. All right, we've done a lot in just the first 2 steps, which is great. All right, step number 3, we now need to determine the real zeros and their multiplicities. So the real zeros are the x values of the x-intercepts. So that would be 1, -1, -3, and 4. If we look at our original function, f of x equals x plus 1 times x plus 3 squared times x minus 4, we can identify each zero's multiplicity. So -1 has a multiplicity, I'm just going to abbreviate it, of 1. So it crosses the x-axis. -3 has a multiplicity of 2. So it touches the x-axis. And 4 has a multiplicity of 1. So it crosses the x-axis. For number 4, we need to identify the turning points. So the number of turning points equals n minus 1. And n minus 1 equals 4 minus 1 because our degree is 4. Remember, n is the degree. So the number of turning points is 3. So for step 5, we now need to just identify other points that establishes the y-axis scale. So we're going to draw our x-axis, and we have 3 x-intercepts. We have -3, -1, and 4. So we're going to identify numbers in each of them to help us graph our function. All right. So I'm going to choose -4. I'm going to choose -2, 1, and 5. So I need to find f of -4, f of -2, f of 1, and f of 5. Okay, and so let's get our calculator to help us. All right, so I'm going to go to y equals. I'm going to clear the function that was there and add in my new function, x plus 1 times x plus 3 squared times x minus 4, and press enter. I'm going to go to the table because I need these values. So second table. Oh, it's still going by 0.5, but that's okay. So I can go to -4 and I have 24. If I go to -2 here, I see 6. If I go to 1, I see -96. And if I scroll all the way down to 5, I see 300. and 84. Okay, so let's jot down those numbers. So 24, 6, negative 96, and 384. Okay? So those gives me the points negative 4, 24, negative 2, 6, 1, negative 96, and 5, 384. Okay, ready. So now let's graph. So I'm going to bring down my intercepts that I have, which were 0 and negative 36, negative 1, 0, negative 3, 0, and 4, 0. So I'm going to graph those first. So negative 3, 0, and then I have negative 1, 0, and I have 4, 0. My y-intercept is negative 36, so it's going to be symmetry here. So I've graphed all my intercepts. I am going to now graph my 4 other points. So I have negative 4 and 24. Well, I'm up to 24. No, here. And then negative 2 and 6. It's 10. And then 1 and negative 96. And 5 and 384. That's way here. So that's way off in the graph. So there's no way that that's there. Okay. So there is another value though, because this point at 1, negative 96 doesn't seem like it's the turning point. So I'm going to go back to my table and try and find a point or negative 2, negative 3, whichever one is lower. So 1, 2, and 3. Okay, here we go. So my y's, they're decreasing, negative 26, negative 150, negative 158, and then it pops right back up. So it's actually between 2.5 and 3. So I'm going to take that 2 or 2.5, and I'm going to graph that value just for an estimate. Okay. So let's do 2. So 2 is 150, negative 150. Okay. So I did f of 2 equals negative 150. All right. So I can use that as my turning point to help me. All right. So I know for my zeros at negative 1, I'm going to cross at negative 1. Okay. I know at negative 3, I'm going to bounce. And at 4, I'm going to cross. Okay. So let's connect all of our points. This goes all the way up to infinity, which resembles the graph x to the 4th. All right. That's awesome. So just to check, to make sure that we graphed it correctly, let's check it on our graph. Okay. So we have our function entered in already, but I want to make sure my window matches the same window here so that I have a more accurate representation. So I'm going to click window, and my x minimum is negative 5. My x max first is 5. I'm going by a scale of 1. My y min is negative 180. My y max is 60, and I'm going by a scale of 20. Okay. Now I'm going to press graph, and I should see a similar image to what I have, and I do. Obviously, the calculators looks a lot more prettier, but at least I know I graphed it correctly. Awesome. Okay, objective 2. Graph a polynomial function using a graphing utility. So for polynomial functions that have non-integer coefficients and for polynomials that are not easily factored, we use a graphing utility earlier in the analysis. This is because the information that can be obtained from algebraic analysis is limited. So for our next example, we're asked to analyze the graph of the polynomial function f of x. So first, let's determine the end behavior of the graph. Well, our leading term is x cubed. This tells us that our polynomial has a degree of 3, and our leading coefficient is 1, which is positive. So our end behavior is going to go to negative infinity and then positive infinity, where our graph resembles y equals x cubed. So we got all this information just from our leading term. All right. Next, we're asked to graph the function using a graphing utility. So let's graph this function with our calculator. So let's go to y equals. We're going to clear what was there before. Then we will enter in our function x cubed. So to get to cube, we'll press math, and we will either select number 3 or scroll down to number 3, plus 2.84x squared minus 4.2251x plus 2.34856, and press enter. Okay. So we want to graph this function. So now we are going to press graph, and it kind of is shown here. Not really. Let's see it a little bit clearer. So we'll go to zoom and let us select, let's see. Let's do number 6, zoom standard. Okay, this is zoom standard. And we see here that this visual does not show our turning point up at the top, but we'll be able to identify that shortly. Okay. All right, so for step 3, we're going to use the graphing utility to approximate the x and y intercepts of the graph. Okay. So let's pull up our calculator. So to find our y-intercept, we know that the y-intercept we substitute in 0. So we're going to go to second trace because we want the calculator to calculate something. So to find the y-intercept, you're going to utilize number 1, which is the value. Okay, because we want to substitute in an x and we want it to tell us a value. So for the y-intercept, we're going to select number 1, and we are going to substitute in 0 for x because that's what we do to find the y-intercept. And it tells us that our y-intercept is 2.34856. All right, so let's jot that down. The y-intercept 0, 2.34856. Okay. So now let's find the x-intercept. right? So now we're going to go back to our calculator and we're going to go second trace again to calculate it. And so now we're going to find our zero because we know zeros are our x-intercepts. So we'll go down to number 2 and press enter. So we're going to locate where the x-intercepts are located on our graph. And I see one here on the left side. So I need to use my arrow to drag that point all the way down to the left side of my x-intercept, which would be here. You can choose any one that's on the left-hand side, any point, but closer to your x-intercept. It doesn't have to be too far away. And I'm going to press enter to select that value. Then I need to go to the right side. So that's, in this case, is going to be to the right of my x-intercept. All right. And then I'm going to try and guess. So it's kind of hard to guess in this case because of how it's jumping. So I'm just going to select this answer now, and it gives me an approximate. So it says my zero approximately is negative 4.032268. So my x-intercept is negative 4.032268. Okay, so I have approximated my y-intercept and my x-intercept. So now it will like us in step 4 to use the graphing utility to create a table to find points in the graph around each of the x-intercepts. So I only have one x-intercept, and that was approximately 4.03. So let's look at -5 and -2 for other values. So I need to find f of -5 and f of -2, and it would like for me to utilize the table. Okay, so let's pull up our calculator. Okay. So let's go to the table. And it's still going by 0.5s, and that's okay. If you'd like to reset it, you can press second window and change your table change to 1. And then go back to table. Okay. So -5 would be negative 30.53, and -2 would be approximately 14.16. Okay, so let's enter that in. So this one is -30, and 14.6. So these will give us the points -5, -30.53, and then -2 first, and then 14.16. Alrighty. And then next we're going to approximate the turning points of the graph. All right, so for this one, we are going to need the calculator to show us what exactly those turning points are. Okay, so we are going to have to make our y-axis a little bit longer so that we can see what that turning point is. And then we can make the negative y-axis a little shorter. So let's go to our window, and we're going to extend this max. Let's go to 15. And then this one we can go to, let's go to 5. And then press grab. Ooh, now I see it a lot better, which is great. All right, so let's find our turning points. I see here that I have 2 of them. And so now we need the approximate values of those turning points. So we can go back to second trace, and we want to now calculate some of the minimums maximums, or you can also trace to try and get the exact values as well. So if we trace, we can just move this cursor to the values. And I see here that it's going to be in between these numbers. It's not exact, it's just an approximate. And then you can do the same thing. So if I do calculate and I go to number 3, I want the minimum value. So I'm going to move a little bit to the left and press enter, and then move to the right and press enter, and then I'm going to make a guess. And it's going to tell me what my minimum is, which is 0.57 and 1.04. Oops, so let's write it down. So our min 1.7 and 1.9. Okay. Now let's find our maximum. Again, you can use trace, but using min and max features will be more efficient. So let's go second trace again, and now we're going to go to maximum. Okay. And so now we're going to go all the way up here, and we want the left side. So here, enter, and right side, enter, and then we will make a guess. Enter. All right, and it tells us our maximum is approximately negative 2.46 and 15.04. So our max, negative 2.46, 15.04. So those are our maximum turning points. So now we're going to use the information that we got from steps 1 through 5 to draw a complete graph of the function by hand. Okay. So let's just compile here all of our points. So that's our y-intercept, and then we got our x-intercepts. Our chosen values here and our turning points. We're going to add all of our points. Okay. Alrighty. Okay. So I have included here our another point, so the -4, 0.69, to just kind of help bring our whole table together. Okay, our whole graph together, sorry. So let's plot some of these points. Alright, so this point, and then our next one is -4.3. And then 0.57, but it goes up to 1.05, and then -2, and then 15.24, and then -5, and 30. I believe that's supposed to be positive 30, yep. But there's no 30 on this graph. So that's going to be rather, nope, it's supposed to be negative because it's going down. So negative 30.53. 30.53. Okay. All right. And then we have -2 and 14. So the other one was negative 2.46. So that needs to move over a little bit. It's not at exactly negative 2. So it's almost at negative 2.5. So right there. And then this is negative 2.14. So it comes down. Okay. And then my other one, which was a negative 4.069. Oh, right here. Okay. And we had another number to on this side right here. We'll need another one on the right side of our x-intercept. So let's go to our table real quickly. Table. So we need one to the right of 2. So let's do 2 and 13.25. Okay. 2 and 13.25. That way we can show our end behavior. All right. Great. So let's connect our dots. All right, we know there's a turning point here. And we know it crosses here. It's the only two. Oh. Connect dots. Connect the dots. Excellent. So beautiful. All right, for step 7, from the graph, find the range of the polynomial function. Well, the range is going to be all real numbers. So from negative infinity to infinity. Okay. Then for 8, use the graph to determine where the function is increasing and where it's decreasing. Okay. So if we were looking at this graph, the increasing values will be from negative infinity to negative 2.46. Then from negative 2.46 to 0.59, it's decreasing. And then from 0.59 to infinity, it's increasing. So let's write that. So increasing intervals is parentheses negative infinity to negative 2.46 and 0.59 to infinity. And decreasing intervals is negative 2.46 to 0.59. Okay, so we utilize the x-coordinate. That's where I was trying. We utilize the x-coordinate to determine the increasing and decreasing intervals. All right, so in summary, step 1, we determined the end behavior. I have the graph, so this is when we're using a graph utility to analyze a graph. Then we graph the function in step 2. For step 3, we utilize the graphing utility to approximate the x and y intercepts of the graph. Step 4, we use a graphing utility to then create a table to find points on the graph around each x-intercept. Step 5, we approximate the turning points on the graph. Step 6, we use the information in steps 1 through 5 to draw a complete graph of the function by hand. Step 7, from the graph, we find the range of the polynomial function. And then in step 8, we use the graph to determine whether the function or where the function is increasing and where it is decreasing. Okay. Alrighty. So objective 3, we are asked to build cubic models from data. So previously we found the line of best fit and the quadratic function of best fit for appropriate data. It is also possible to find other polynomial functions of best fit. However, most statisticians do not recommend finding polynomials of best fit of degree higher than 3. Data that follow a cubic relation should look similar to the scattered plots below. Notice that these scattered plots resemble the x-cube function. Okay? The first one has an a that is greater than 0, and the second has an a that's less than 0. So remember, a is the leading coefficient of the leading term. So in our example, we are told that the data shown represents the monthly cost C in thousands of dollars of printing X thousand brochures at a marketing company. A tells us to draw a scattered plot of the data using X as the independent variable and Y as the dependent variable, and then comment on the type of relation that may exist between the two variables X and C. And then once we have drawn that scattered plot, we are going to do B, where we're going to use a graphing utility to find the cubic function of the best fit that models the relation between the number of brochures and cost. Okay. So the first thing that we need to do is grab our calculator. All right. So now we're going to enter in this data. So we are going to go to Stat, and we're going to go to Edit. And in List 1, we're going to enter in all the values in our first column. List 2, we're going to enter in all the data values in the second column. So let's enter that in: 0, 5, 10, 13, 17, 18, 20, 23, 25, 27, and then we have 10, 12.8, 14.4, 15.5, 16.2, 16.6, 16.3, 17.8, 19.2, and 22.8. Okay, and then you want to check to make sure everything matches up. Remember, list 1 represents the number of brochures in thousands, and list 2 represents the cost in thousands of dollars. All right, so now we want to create a scattered plot. So we're going to go to y equals. We are going to clear our previous function that we had in there. Now we're going to go up to plot number 1. Make sure it has plot number 1 selected. And we're going to press enter. Okay. Now we need to set up plot number 1. So we're going to go second y equals, and we turn on plot number 1, but we want to make sure that all the settings are there. So we're going to enter into plot number 1. It's turned on. We want our type to be scattered plot, which is the first one here, which is great. Our X list is our list 1. and our Y list is list 2. If these weren't the correct lists, you would have to go to list here above stat. So you would press second stat and then select a different list and it would change. Since I want it to be list 1, I'm going to select list 1 back. Okay, then list 2. Now for the marking on your graph, you can do whichever one you would like. I'm just going to keep it on the first one. And then if you have the color option, you can select a different color. Okay? Once you have all of that on, we are now going to graph. Okay? And you see here on your graph, we don't see all of our point values. So we want to make sure that all of our point values are there. So we're going to go to zoom, and now we want to go to zoom stat, which is number 9. And we see all of our data values. Okay? And so this scattered plot resembles a cubic relation. So for a cubic relation may exist between the two variables. So a cubic relation may exist between the two variables. Okay. Now we want to find the cubic function. Okay. So to do that, we're going to now go to stat. We're going to go over to calc. We wanted to calculate something for us. We've identified it as a cubic relation. So we're going to go to number 6, cubic reg. Okay. And we're going to select enter. Our X is in list 1 and our Y is in list 2. Again, if it's in a different list number, you can just change it by selecting second stat. We're going to leave frequency alone and store reg equation alone, and we're going to press calculate. Okay. Now we have calculated the cubic relationship for our data points. So it's written in standard form. Our A, B, C, and D are our coefficients, which we will then substitute into the standard form to have our equation. Okay? And so we are going to round to 4 decimal places for each one for our equation. Okay? So we will have C of X equals 0.0018 x cubed minus 0.0673 x squared plus 0.988 x plus 9.7737. And that would be our cubic function for our data points. Okay. All right. So graph the cubic function of best fit on your scattered diagram. So now in our calculator, we're going to enter in this equation into our y equals. Okay? So we're not going to turn anything off. We're just going to enter that equation straight in. So we have 0.0018 x cubed minus 0.0673 x squared plus 0.988 x plus 9.7737. And we'll enter that in, and then we'll press graph. And we see our best fit right over our scattered diagram. This looks cool. Oh, it looks so cool. All right, so we have graphed the cubic function over our scatter diagram here. And that is what C asks us to do. Now D says use the function found in part B to predict the cost of printing 21,000 brochures per month. Now the 21,000 brochures per month is going to be the X, because X represents brochures in thousands. So we want to find C of 21, all right? And we can use the function to help us. So we're going to substitute in 21 into our function. Okay? So by hand, you would substitute in 21 and evaluate that function, or you can utilize your calculator that has that function to help you. Okay? So we want to find a value. So we're going to go second trace and we want to find a value. And we want that value to be when X is 21 and press enter. And we get 17.5122. So 17.5122. So what does that mean? Well, the cost of printing 21,000 brochures per month will be $17.512 thousand. That is $17,512. All right. Whew, that was fun. I hope you had some fun. Okay, that concludes section 3.2.